let's try and understand a bit of circular motion in depth. Alright, now suppose this is moving this way, alright, obviously anti-clockwise. Then these are all vectors. Alright, direction of alpha omega is always upwards. Alright, it's always upwards. Anti-clockwise, it's always upwards. Alright, this is the angle covered theta. Alright, I had shown you this. Now I'm showing it like this. Alright, so it's moving like this. So this is the arrow that I'm pointing towards. This is the arrow that I'm pointing towards. So towards upward direction is omega, the angular velocity and angular acceleration. Got it? And this is, suppose, is the angle covered theta. This is the radial vector which moves from center towards the circumference of the circle. Fine? Okay. Now, this circle has got both linear and rotational acceleration. It has rotational motion as well as linear motion. Can you tell me where? See here. So when we are talking in terms of circumference, if I open up the circumference, that becomes 2 pi r. So that is what is linear. Linear thing is over here. And where is the rotational thing? Rotational thing is over here. This part is rotational thing. Take it. Okay. So linear. So this is linear acceleration. We call it as tangential acceleration. Alright. Now tangential acceleration. The formula for tangential acceleration is r alpha. Alright, r alpha. Now see, here you had seen the conversion factor, right? So this is actually, we can call it as tangential acceleration. Alright, is r alpha. Alright, now let's talk in terms of radial acceleration. Now when we are talking in terms of circular motion, you know that there are forces acting, one which acts towards the center, we call it as centripetal force, and one which is acting outside, we call it as centrifugal force. Alright, so we are dealing, and force, formula for force, you know, is ma, right? So here the radial acceleration is minus r omega square. Now mind you, if I am pointing it towards inside, since I am pointing it towards the center, so I put in this negative. Negative is just depicting its direction. Alright, that its direction is towards the center. Alright, okay. So we can avoid that right now for our mathematical derivation of formula. Okay. So now see, this is AR is equal to r omega square. Omega, we come back here, V is equal to r omega. Alright, so if V is equal to r omega, what would omega be? Omega would be VO, omega would be V over r. So instead of omega square, I substitute V over r the whole square. So 1 r, this r disappears and this square gets converted to r. So our formula would be V square over r. If we want it in terms of linear, now the calculations, now numericals that you may get, they may ask you angular velocity or linear velocity. So if you are intending to calculate linear velocity, so you are supposed to know the conversion factors. Alright, so we use the conversion factor and AR, which was in terms of angular format, r omega square changed to V square over r, which is in linear format. Alright, so both of these accelerations are either centripetal acceleration or centrifugal acceleration. Alright, so it's moving in a circular motion. Why? Because centrifugal and centripetal forces are in equilibrium. That's why it's moving here in a circular motion. Alright, so I just did a small derivation. So F is equal to ma, mass into acceleration. Now it could be FCP, it could be FCF. If it is FCP, it would have negative sign, and if it is FCF, that is centrifugal, it would be towards outer, would be positive. So F is equal to ma. So if I'm talking in terms of this, would be minus, right? If I'm talking in terms of centripetal force, this is showing the direction of acceleration. Alright, that it's towards the center. Okay, so FCP is equal to mr omega square, and it could be v square over r also, so it could be mv square over r. I hope this part is clear. All right, okay.